So now for our next major types of reactions, we're going to be talking about a bimolecular elimination or an E2 reaction. E2 reactions are going to have a lot of similarities to SN2s, much like how E1s and SN1s are similar. First and foremost, they are both concerted, that is an E2 and an SN2. Concerted is a reaction where everything happens all at the same time. If we were to write out our rate equation, or our rate law that describes the kinetics or how quickly this reaction happens, it's going to look a lot like our rate expression for SN2. It's going to be equal to our rate constant times the concentration of our base, and then our leaving group. One noticeable difference here is instead of having nucleophile, we're going to have a base. One of the biggest differences between our SN2 and our E2 is going to be thinking about that negatively charged thing. Is that more nucleophilic or more basic? If it's more nucleophilic, it's going to go SN2. If it's more basic, as in it wants to abstract a proton, it's going to go E2 and eliminate. These are going to follow most of the same rules that we talked about previously, especially like the idea of Zaitsev's rule. So if we wanted to think about a mechanism, you're going to have a base, often with a negative charge. That is going to come and it's going to abstract a proton. That proton is going to be exactly one away from a leaving group, in this case a bromine. As it abstracts that proton to form a conjugate acid, which is just going to be the protonated base, which you'll see like over here in ethanol, that would be your conjugate acid. This is a base. As it forms that conjugate acid, it is only taking the proton. That means there are no electrons going along with it. So the two electrons that are in that bond are going to go to towards that leaving group, and that's going to make a double bond. As that double bond is being formed, that would then violate the octet of that carbon, so that leaving group is going to peace out. And you'll have all three arrows, new bond being formed, double bond being formed, and then bond being broken. And that's going to make a double bond on your substrate, and then giving you your leaving group with a negative charge from the lone pair. Now, if we wanted to go through and get practice kind of predicting a product with this, we could consider, for example, this structure here. Here we have a strong base of our ethoxide ion. Ethoxide because it's F as in 2, and then the oxide from being the deprotonated ethanol. That's going to come and subtract or remove or deprotonate our structure. In this case, there is no favorability in terms of Zaitsev's rule. The hydrogen on the other side, so if you had like this hydrogen over here, are equivalent. So you can abstract either, and there is no preference, so you're only going to get one major product. Let's actually show a different arrow for that, different color. You will have a deprotonation, forming double bond, leaving group leaves. And that would give us our product that would look like this. And then your other products, which you don't need to draw, would be like your ethanol and then your Br minus. Now, we've talked about naming the past, but if we wanted to do a quick refresher, I have 1, 2, 3, 4, 5 total carbons. So that's going to carry a pent, and it's going to be an ENE corresponding to the double bond. If I do our numbering, I would do 1, 2, 3, 4, 5. And the 2 position, I want to count in that direction because I want to get to the double bond as quickly as possible. The 2 position is the first time I see my double bond, so I'm going to call that 2-pentene. You could also call that pent-2-ene, same idea. Now, much like how in a SN2 reaction, we had a very specific type of directionality of the attack. We call that a backside attack, where your nucleophile came in the opposite direction of where that leaving group was leaving. And that was kind of needed because you didn't want to create a traffic jam. And as a consequence of that, you got a inversion of your configuration, so your wedges and your dashes changed. That same general idea also happens in E2. However, we don't call it a backside attack. We have a very specific name, and this is this idea of anti-periplanar. And anti-periplanar is going to describe the direction of attack for that deprotonation. Much like how your SN2 wanted to come from the backside, your deprotonation is also going to happen from the opposite side. So here, if we kind of think about where the leaving group is and where that hydrogen is, you're going to actually abstract a hydrogen that's going to be on the opposite side in order for a few things. First, for your orbitals to actually overlap. You actually see some coloring in there for your phase. You need to have the correct phase in order to actually make your double bond. And you also want to have that proper kind of like spread, so you don't have that kind of like traffic jam of where you're trying to extract the hydrogen as well as that leaving group leaves at the same time. This actually creates something that's a little bit interesting, especially when we think about chairs. And we will definitely be doing some eliminations on some 6-membered or some cyclohexane rings. And with that, the amount of hydrogens you can actually abstract is actually a little bit different. So here I have an example of a chair, and we have a leaving group here being in a bromine. That leaving group is in a axial up position. Anti-periplanar is going to be a opposite direction, and for that, your opposite direction is going to be an axial down. And here there are exactly two, maybe we'll show this in green here, axial down hydrogens, which are in the opposite direction, exactly one bond away. And if we were going to do an elimination on this structure, you would actually only abstract one of those two highlighted hydrogens, and you would not be able to actually abstract either of the equatorial ups that exist on that structure. And you can actually see a really interesting structure. And we're actually going to draw an example right now. So let me go and scroll down to that. So let's go ahead and consider this structure here. And we've actually seen a pretty similar structure on our E1. Let's go ahead and think about what this structure looks like in regards to a chair, because this is a cyclohexane, and we need to think about what hydrogens are actually available. In an E1, it doesn't really matter because you're doing it in 2 steps. That leaving group leaves, and then you're going to get your deprotonation. So you don't have that traffic jam. In a E2, when everything all happens all at once, you do actually need to really pay attention to that directionality and make sure that you have anti-periplanar hydrogen and leaving group. So let's go ahead and draw the chair conformation for this. So I'm going to start by drawing just a base chair, 2 slanted horizontal lines, and then I have my 2 vertical ones, and then we'll go ahead and complete. So there's my base chair. And let's go ahead, and to make things a little bit easier, I'm going to go ahead and define my chlorine being in the 1 position, and we have a wedge, which we're going to describe as up. So I'm going to go ahead and put that chlorine in an axial up. Your leaving group is not going to do a very good job leaving in the equatorial. So you're almost always going to have an axial leaving group. So I'm always going to define my leaving group kind of in that like top position. Now, if I kind of look at my other groups, 2, I have nothing. At my 3 position, I have a methyl group that is going to be also in the up position because it is also a wedge. So if I go 1, 2, that would come over here. So I would have a CH3 that is in the up position, and that's going to be an axial up. And then at the 4, 5, 6 position, I'm going to have a down. And that down position is going to be right here for that isopropyl. So those are the different groups that I have on that structure. Now let's go ahead and consider what spots I can actually do an elimination. If you remember from the first discussion of when we called it an elimination, we called it a 1-2 or a beta elimination. And for that, we can only abstract protons, which are exactly going to be 1 bond away from my leaving group. So if my leaving group's at the 1 position, I can only abstract protons at the 6 position and the 2 position, exactly 1 bond away. At the, let's go ahead and put these in a different color. If I look over at the 2 position, I have a proton, which I can call HA, which is going to be in an axial down. And then I also have an equatorial, which I can call HB. And that's going to be an equatorial up. At the 6th position, I already have something in my down position, so I only have something in my equatorial up, which we can call HC. Now, if I look at all of these hydrogens here, there is only a single proton, which is my HA, which is in this anti-periplanar, where I have 1 up and then 1 down for my reference to where my leaving group is. So here, we cannot, emphasis on the word not, use my HB or my HC for my elimination, because those are not anti-periplanar. The only one that I could abstract is going to be my HA. Now, this is actually going to be a relatively slow reaction in comparison to some others, because you'll notice my HA is kind of being blocked by this isopropyl that's connected to the 2 position. So if I have a base, my base is going to have a really hard time if it's, for example, over here. Because if it's trying to attack, there's going to be some steric clash with that isopropyl, and that's going to make that reaction slower. So I have a base over here. It's going to abstract my HA. Those electrons are going to go into the bond, and then my leaving group is going to leave. And there's the way in which I'm kind of showing this chair-like structure and my mechanism at the same time. Now, if I'm going to draw my product, I can only draw my product as an actual ring. I'm not going to draw my product as a chair, because we're going to have issues with my bonds in terms of my angles. So if I'm kind of thinking of what my groups are, the hydrogen that we eliminated, my specific HA, is a dashed, because it needs to go down over here. And our bond is going to be formed between my HA, my 1 and 2, and my chlorine. So if I wanted to draw my product, I would then have my double bond here. I would have my wedge over here. And then I would have my dashed for my isopropyl. And this right here is going to be our major product. Now, if you remember it all the way back when we talked about E1 reactions on this exact same substrate, we actually talked about forming the double bond over in, let's go and get a different color here, yellow. We talked about forming the double bond in like this position in the E1 to follow my Zaitsev's rule. However, that location, which is going to be like right there, I can't actually do any chemistry because I'm not anti-periplanar. And that's going to have some really important considerations for our structures. And we're going to show a few more examples in class and work through and get some practice of trying drawing some chairs. Let's go to do one other kind of quick example where we can think about this anti-periplanar nature, but not have to worry about actually drawing chairs. So let's go ahead and consider this structure here. Here we have a structure of kind of a pretty simple, we only have just a few carbon system. Now we have some words here. So we have a pH. If you're not familiar with that abbreviation, I'm not sure if we've actually formally gone over it. So pH is an abbreviation for phenyl, P-H-E-N-Y-L, and phenyl is going to be a benzene ring where you have a connection. Drawing a giant benzene ring is a little bit complicated, so we just abbreviate it as pH. So here we see we have a structure, and we have an anti-periplanar structure here of hydrogen, a bond, and then a bromine. So if I have a base, I can come in and I can do some E2 chemistry. This is going to have a big impact on our stereochemistry, especially with our E and our Z configurations. So if I have my base, which is going to be my ethoxide ion, and it will come through make a double bond, and then make the bromine, we are going to overall have a structure that's going to kind of look like this, where I have my double bond and then my two different attachments on each side. For my attachments, I have a phenyl, a methyl, a hydrogen, and a phenyl. And where those phenols are located is going to be really, really important, because that's going to change whether or not you formed an E or a Z. Here I see that my phenyl was a wedge and a wedge, so they're on the same side. So my wedges are going to be on the same side. So I'm going to have a phenyl and a phenyl. And then my dash stuff, which is going to be my CH3 and my hydrogen, are also going to stay on the same side because they're both dashes. So my dashes are going to be on the same side, and then my wedges are going to be on the same side. Every once in a while, you might get a reaction where you have a hydrogen that's not anti-periplanar, and then you might need to actually take and then spin or rotate and draw a new conformation, and that would give you, again, very specific stereochemistry. Now, if I think of my stereochemistry here, my phenyl and my phenyl are going to be on the same side of the double bond, and the same side, or same side, if you remember that kind of shorthand, is a Z configuration. So this reaction here, if we do an E2, is only going to form a Z. You will not get any E, because the E would not give you an anti-periplanar configuration. So let's go ahead and summarize a few things we're thinking about when we're thinking about our E2 reactions. So E2 reactions are going to be concerted. They're all going to happen at the same time. You're going to have a strong base. Most of the time, you're going to see things like this sodium ethoxide. T-butoxide is going to be another kind of bulky base that you'll see. In a single step, you're going to have a total of 3 arrows. You're going to have a protonation, deprotonation. So that is our first arrow of abstracting that proton over to your base. The electrons in the bond between your carbon with the 2 position or the beta position, that's going to be 1 away from where your leaving group is. Those electrons are going to go into the bond between carbon 1, carbon 2, and that's going to form a double bond, and your leaving group is going to leave. All 3 of those arrows are going to happen at the same time, and you're going to get your conjugated double bond, and then you're going to get your conjugate acid and a leaving group. This is going to happen in an anti-periplanar conformation. We can think of this as one of 2 ways. In your normal kind of zigzag alkanes, you'll need to make sure that your structure is in that type of configuration, and that's going to impact your stereochemistry, your E and your Z. If you have this on a cyclohexane ring, you need to make sure that these are going to have an axial up and an axial down for your leaving group and your hydrogen, and that will actually dictate what products you can actually get. And this might be an example where you might want to instinctively try to draw something in a Zaitsev rule, but that Zaitsev rule is actually not even possible based on that configuration. And those are some kind of our key highlights associated with our E2. In our very next video, we're actually going to walk through a few other reasons why you might not get an apparent Zaitsev rule follower in your reactions, and we'll talk about 2 different examples of conjugation and Hofmann. And that kind of wraps up a lot of kind of our key concepts about our elimination reactions. Where it gets really interesting, and what we're going to spend a bunch of time in our next class talking about, is the comparison between, if you have a specific reaction, will it go SN1, SN2, E1, or E2? And thinking about a matrix where all 4 of those are possible choices. But I think that's a good spot to kind of end our kind of introduction to E2. And we'll get some more practice in class and talk more about some of our Zaitsev rules in the next video.